Hello, my name is Dimanov, and it is my honor and great pleasure to present our work with my colleagues called MEOW, which stands for Automatic Evolutionary Multi-Objective Concealed Weapon Detection Technique. The core principle behind MEOW is the application of neuroevolution to conduct neuroarchitecture search specifically tailored for convolutional architectures in the realm of security. We've ventured deep into X-ray computer vision, a domain where data significantly deviates from visual spectrum, necessitating specialized techniques and architectures. Now let's discuss why we've created MEOW, how it works, and how good it is. I'll start off with answering why MEOW is needed. Firstly, there is a need for custom X-ray architectures, and while ResNet ones have achieved somewhat good results in medical and security applications, the need for specific architectures is becoming more and more apparent as the research field grows. These systems hold paramount importance in industry, especially when you consider that medical and security imaging devices play a pivotal role in decision-making processes. But there's a challenge. Crafting such domain-specific architecture demands a multidisciplinary team, extensive human hours, and even more computational ones to train the models, discern patterns, implement these patterns, test their generalization capabilities, and so on and so forth. Furthermore, the architectural requirements can vary across X-ray datasets. For instance, the architecture suitable for a brain scan data might not be optimal for an X-ray bag one, like the one on the screen. This is where AUTOML and neuroarchitecture search come into play, offering a solution to this gargantuan task. However, a significant drawback is the inefficiency of most neuroarchitecture search algorithms that take days and sometimes months to compute. The general paradigm of algorithms we use in this work is neuroevolution, which follows mostly the principles of evolutionary algorithms, but has these few extra steps, encoding and decoding, which ensure the neuroarchitecture is first encoded into a compressed genotype and then decoded as an architecture in order to be evaluated. The step that usually takes 99% of the time is the evaluation step, where the newly produced models need to be trained for some epochs before being evaluated. This is extremely inefficient, and recently a few works like neuroarchitecture search without training and SynFlow have provided accelerated ways of estimating how good an architecture is without training it at all. Next, I'll discuss how these cores work in general, but the most important part for understanding MEOW is to know that neuroarchitecture search without training one uses a batch of data to determine the performance of the network, while SynFlow, the other one, is data agnostic and it uses a batch full of maximum values once. The NASLOT estimates the performance of a neuroarchitecture based on the similarity between inputs for a given architecture. It uses symmetric matrix that represents the similarity between inputs for an architecture comparing each to the other one. The more dissimilar the binary codes associated with each pair of inputs are, the easier it is for the network output layer to discern between them. NASLOT score is essentially a measure of how well the architecture can differentiate between different inputs, comparing each pair. SynFlow, on the other hand, is data agnostic score that focuses on weight values of the network rather than the activations, like NASLOT. The network is stimulated with a white image or a tensor of ones. In this setting, a low dependency of the network output, there is low dependency of the network output on weight magnitudes as a proxy for the architecture's high discrimination capability. It indicates how the importance of each parameter, each weight in the network and determining the output, and the sparseness in irrelevant connections leads to more selective paths of information processing. In summary, while Naslot evaluates architecture based on their ability to differentiate between inputs, SynFlow assesses them based on their weight values and how they influence the network's output. Here's a general overview of the process and the important parts of MEOW on the figure from the paper. First, we have the encoding of the whole population of architectures in A. In B, we have a decoded architecture, and in C, we have some of these activation maps used by Naslot. In D, we see a sample input used to generate the predictions in F. Finally, in E, we see all objective values assigned to a particular encoding. Notice that we have three different objectives that we optimize for simultaneously: the two proxy scores and a level of complexity, which is a metric that is reversely proportional to the size of the network in terms of parameters. To ensure we don't just use the best architecture from the generated approximation set based on contributing hypervolume, we also come up with an ensemble approach that uses multiple of the produced architectures. Now let's see some results. On the bottom you can see a NASL 6-ray example, and we evaluate MEOW on two main datasets: 6-ray, which is a multi-label dataset with the possibility of multiple thread items in each scan. In fact, 6-ray is the largest X-ray dataset with more than a million images, and you can see a sample of them on the screen. They contain different baggage items and different threads. In the table, we can see how MEOW discovered the architectures that perform compared to the state-of-the-art ones, and we can see that these architectures outperform by some margin all state-of-the-art ones. It is important to note that MEOW architectures are smaller and faster than their state-of-the-art counterparts as well. The next dataset that we test the approach on is a proprietary dataset we call Residuals, provided by our industrial partners Counting Lab, which is a multi-input, multi-output dataset where a couple of images are used to make two separate predictions of a potential modification as well as a potentially discovered threat. Here, again, the MEOW discovered architectures outperform the other models, and interestingly, with this dataset called Residuals, the benefits of the ensemble approach are less apparent than in 6-ray, but still it achieves the best scores throughout. As part of our results, we also provide a level of granularity of the results for both of the thread predictions as well as the modifications, which is currently presented on the screen. Interestingly, there are some cases where the most contributing MEOW architecture outperforms the ensemble approach, and we can also see how close MEOW architecture scores really are to the ones of Inception ResNet v2, and still they outperform them despite being significantly smaller. We also test MEOW's ability to discover segmentation models, and thanks to the provided labels as part of the proprietary dataset, we are able to evaluate how it does when compared to some of the best UNet architectures, which is currently on the screen. While here MEOW does not achieve the highest test IOU or F1, it is still in the top 3. More importantly, MEOW architectures has only a fraction of the parameters of the other approaches as seen in the first column, and is one of the few edge-compatible architectures on the list. When compared to similarly sized models, which are still more than 10 times larger, it does outperform them by a large margin. However, the most important thing to observe is the reliability of the MEOW model, because it is the only model that performs consistently on the validation and test set, which shows that it hasn't overfitted to the dataset, and it shows the greatest generalization capabilities. The most striking feature of MEOW is its efficiency. All runs for all models are discovered to consume only less than 1 GPU hour. No training is done during the discovery process, which means that instead of waiting for multiple GPUs for days, now such architectures can be discovered in a matter of hours, even on a non-GPU machine. I'm happy to talk in much greater detail about the paper, so please reach out to me during the event or with the correspondence email. Thank you very much for your attention and have a nice time in Berlin. Thank you. Bye-bye.